surface and reaches the receiving antenna. In addition to the direct signal, the reflected signal arrives at the receiving side. In some cases, the reflection of the microwave signal from their surface is quite critical. And yeah, for example, fluctuations in the power of the incoming signal at the receiving and over a long period of time. Second, it's amplification of multipath propagation activity. Third, decrease in the effectiveness of the spatial diversity technique used in the using as a mean of multipath propagation. So in the process of planning the communication link, as far as possible, reflections from the ground surface should be avoided. Yeah, example is, for example, weather surface is a classical example. Yeah, in some cases, it may be possible to position the antenna in such a way as to obtain receiving of the reflected signal. Yeah, reflections from Earth's surface, yeah, depends also of Earth's surface. So terrain profile. Yeah, in this slide we see station A, station B, so transmitting side, receiving side, and direct signal and signal which propagates reflects from Earth's surface and then arrives to the receiving antenna. Yeah, here is reflection point. So Ni is angle of incidence. Yeah, the direct signal path. And yeah, reflected signal path is sum of R1 plus R2. Yeah, in this case, the vertical antenna orientation is assumed to include the effective ground radius, which is about 133 at the high values of K. The beam will be tilted downward. This will reduce the discrimination angle of the antenna. In contrast, at small values of K, the beam will be rotated upwards, and the discrimination angle of the antenna will be increased. Yeah, in all simulations, this key factor is assumed as a value 4/3. It's like for normal atmosphere. Yeah, all calculations actually assume this value in simulations. Yeah, and this is needed due to the fact that Earth's surface is not flat. Yeah, in longer distance. Yeah. Um, yeah, and to take this into account in calculations, yeah, key factor is used. Yeah, yeah, the effect of reflection and the total received signal is expressed as the vector sum of the direct and reflected signals. And yeah, the results of the sum of two vectors, T and A, depends on amplitude of signals from reflection losses depending on the type of surface, key factor due to the spherical shape of Earth. Key factor depends on the geometry of the profile interval and the antenna beam aperture and other ones as mentioned in the slide. So if antenna height is variable, then the link path length difference and phase shift between the direct and reflected signals will change, resulting in the receiving signal level being a function of the antenna height. If direct and reflected signals are in phase, then at receiving point will be received maximum receiving level of signal. And if direct signal and reflected signal are out of phase at receiving side, then we will receive minimum receiving level. So basically, if signals are out of phase, then they uh, minimize the receiving signal due to this phase shift. Receiving signal level varies with the antenna height, but the position of the maximum receiving level is not stable due to varying propagation conditions. With two antennas, a good receiving level be expected at least at one antenna. Yeah, and yeah, why here is mentioned that key factor may change. Its key factor depends of atmosphere actually. Yeah, and by changing temperature and other weather conditions, yeah, this can have impact on how signals are reflected from atmospheric layers. But for normal signal propagation, yeah, this key value is assumed as be such value. Yeah, therefore is it's preferably to have even more than one receiving antenna. Like in this picture, we see due to different key factor values, signal propagates a bit differently. Yeah, and if we have additional receiving antenna at different heights, then yeah, system is possible to receive, let's say, adapt to these environmental changes and work in uh, optimal uh, optimal way. So, but if as such solution is quite yeah, it's expensive. Yeah, so systems engineered taking into account this normal signal propagation condition. Yeah, antenna spacing. So optimum value is computed, but depends on the key factor. Yeah. So as I said, for this theoretical value is assumed this key factor value, but yeah, in practice, some environmental changes can affect how signals propagate and how signals bending, yeah, at higher atmosphere layers. Next, position of the lower antenna in general as low as possible in order to obstruct, at least partially if possible, the reflected beam, minimize phase difference and the reflected signal delay. And as regards to clearance, for the lower antenna, in most cases, the clearance from obstacle is zero, is sufficient. The position of the highest antenna is calculated using usual rules. Yeah, in case of this space diversity approach using several receiving antennas, yeah, it's possible to configure when signal processing is switching to the best signal received by adaptive combining of these yeah, and combining if signals are in phase, then signals are uh, uh, signals are with higher receiving power at receiver. Yeah, and reflected beam delay that must be compared with the symbol period of the signal. Depending on these values, the reflection effects are the following. Um, reflected ray delay is much smaller than symbol period. Uh, Yeah, this is case for variation in the receiving signal level without frequency selectivity in the signal bandwidth. When this next one is when these two parameters are equal, then frequency selective attenuation within the signal bandwidth happens. The maximum in-band dispersion depends on the reflected signal level. Measure of receiving sensitivity is determined by the hardware. And third case, when reflected beam delay is higher than simple period. It's like rare condition. In this situation, similar to the external co-channel interference, since the reflected signal is uncorrelated to the direct one. Yeah, and yeah, the equipment gives a measure of the relevant quality degradation. Next, when signal propagates in presence of precipitation, um, the main phenomena here is in this case microwave signal propagation is affected during rain. First is scattering. Some of the electromagnetic wave energy is radiated from the raindrops in all directions. Absorption, when some of the electromagnetic wave energy is transferred to raindrop molecules. Third, depolarization, when momentary change happens of polarization of the signal. In this way, the cross-polarization component occurs in the receiver. So three main phenomena, yeah, due to rain. And the polarization depends on signal frequency. Yeah, in it most is this effect is most probable when wavelengths of signal are comparable to raindrops. Also, this depolarization depends on signal polarization and intensity of rain. So basically, rain can impact microwave signals operation. Yeah, physical, let's say, level. So transmission of microwave signals at frequencies higher than 10 GHz is more affected by precipitation, rain, snow, ice cubes, and can weaken and scatter the microwave signals, and this determines the performance of the system in terms of transmission quality. energy is weakened by radiation and absorption. Absorption attenuation attenuates the signal more than scattering attenuation at wavelengths smaller than the Doppler size, raindrop size. For wavelengths equal to the length of the droplet, the attenuation of scattering is more typical than the attenuation of absorption. Yeah, in this figure, it is presented radio communication link with its Fresnel zone, and this link is crossed by raindrops. Yeah, yeah, and each individual drop brings an attenuation of the valid signal. The actual amount of attenuation introduced depends on the frequency of the signal and size of the droplet. Rainfall is measured in millimeters and rain intensity in millimeters per hour. Yeah, and raindrops shape can be different, let's say, as the size of raindrops increases, their shape changes and becomes different from spherical. And such deviation from a spherical shape causes them to be yeah, let's say it causes them to be elongated in the horizontal direction. Yeah, it's getting longer, let's say. And consequently, the droplets attenuate horizontally polarized waves more than vertically polarized ones. Yeah, horizontally polarized waves. Yeah, it's one of polarization which is used in fixed radio communications systems is horizontal polarization and vertical polarization. There are also other polarizations, but these are typical ones. Also, yeah, for example, also TV broadcasting usually uses horizontal polarization. Yeah, it can be um, very good seen in when you look at the aerial antenna. It's in horizontal plane. The antenna radiators are uh, in most cases in horizontal plane, but yeah, sometimes also vertical polarization is used, but it's most rarely. at least in Latvia, only horizontal polarization is used for TV broadcasting. Yeah, but this droplet affects frequencies, as it was mentioned in previous slide. The effect is most on frequencies above 10 gigahertz. Yeah, and due to this physical phenomena, vertical polarization is best used at high frequencies, where the outage time of microwave link caused by rain is more typical. As the microwave signal propagates through the rain, the signal scattering and absorption appear. In this process, part of the transmitted signal energy is lost, and this can be described with rain attenuation. And in this case, yeah, so as you remember, in case of free space loss, which actually is attenuation by atmosphere, the measurement unit there was decibels. And in case of rain attenuation, the measurement unit is assumed decibels per kilometer. It means how much signal is attenuated at each kilometer. Similar values are used, for example, for uh, coaxial cable. For example, there is cable attenuation, cable introduced attenuation, and measurement unit is a decibel per meter. But here, yeah, in this case, signal propagates in atmosphere. So free space. Yeah, basically, this is a case where additional to free space loss, we need to count also this rain introduced attenuation. And therefore, is actually in radio link budget calculation, it's important to take some this margin for receiving signal level, and to take into account also this effect, rain attenuation. And the rain attenuation increases with increasing frequency, but can be assumed to be constant or uniform within the radio channel bandwidth. Yeah, uh, and channel bandwidth is usually some megahertz, so the situation not changes too much within a channel limits, but yeah, but for each frequency band is calculated such parameter. And rain attenuation increases with increasing rain intensity. For horizontal polarization, this is more typical than for vertical. Causes attenuation, usually for no more than a few minutes. But of course, this depends on how duration is of the rain and rain intensity. Yeah, for example, those who watch, for example, satellite television, yeah, this phenomena also can be observed when weather conditions are not too good. Then also signal quality at satellite receiver is results in bad quality of signal. Yeah, in this case is shown example attenuation due to rain and yeah, this dependency of frequency and rain and rain intensity uh, and result is this rain specific attenuation in decibel per kilometer. We can take okay, let's yeah, okay, 20 and it's about 60 gigahertz somewhere. Okay, let's take 20 gigahertz. So at 20 gigahertz attenuation is yeah, relatively low. At rain intensity such value, but if we go up to higher possible value, rain intensity 90 millimeters per hour, then this attenuation is somewhere 18 decibels could be, yeah, 18 decibels per kilometer. It's value just for kilometer. For example, if your radio link is in length of 5 kilometers, then this total attenuation is quite impressive. And this is just due to rain, yeah. So in temperate climate zones, rain does not significantly affect systems operating at frequencies lower than 10 GHz. But in tropical climates, the effect of precipitation must be taken into account even for 5-6 GHz microlink calculations. ITU has developed a world map of precipitation distribution regions. Each region is assigned a rainfall intensity millimeters per hour for a given percentage of time. And also ITU is prepared recommendation named characteristics of precipitation for propagation modeling. Yeah, okay. This link will be available in okay, I will copy in chat. Yeah, you can open this recommendation and go through. Yeah, this is a fragment of European part. So of this ITU are prepared precipitation map, and this figure is for Europe. Yeah, and if we zoom a bit, we see different lines here, yeah, and some letters provided inside those zones, let's say. We see this letter A, and rain intensity is very small. For example, yeah, this E, where is also Latvia. Rain intensity, average rain intensity is 22 millimeters per hour. Yeah, and basically even relatively small region as Europe, there are quite impressive difference from yeah 60 millimeters per hour up to 8 millimeters per hour. And closer to the equator, these values are getting higher. If we go from north to south here, we see this precipitation values increases. Yeah, and this comply with this figure. So the annual rainfall rate uh, for the world, and the most the higher intensity is with this red color. If you get in this light. Yeah, and this is from the recommendation I sent you. Yeah, and as we noted before, higher frequencies, higher attenuation, and precipitation is not identical in all areas, which is why ITU released a recommendation for splitting the world into 5 regions according to precipitation intensity. In the areas with higher precipitation greater than rain attenuation must be expected and a greater signal fade margin must be established. Yeah, basically, yeah, it relates to budget calculation, so we need to make for countries which are closer to equator, this fed margin or reserve need to be planned higher in value. And the following properties are inherent to rain attenuation. First, it increases exponentially with the rain intensity. It becomes significantly larger as the distance traveled increases, more than 10 kilometers. Horizontal polarization causes greater rain attenuation than vertical polarization. Rain outage increases dramatically with frequency and path length. Yeah, this is another map, but still it's a ITU map. Maybe from visual perspective, it's more more user friendly. So yeah, with colors and legend here. Um, yeah. Okay. This map also includes in previous this picture we have rain intensity up to 90 decibels, but here, yeah, here, in this slide, the rain intensity for Europe was maximal of 60 millimeters per hour. But in this slide is given situation for all world, and we see that there are some areas with rain intensity up to 115 millimeters per hour. This region is here, close to equator. Yeah. Quite impressive difference. Yeah, and for this task, you will have also a homework, and yeah, the task will be uploaded to Ortus. Let's see this time or next time, but in relation to precipitation, we will have one task. Okay, let's do now 15 minutes break and then we'll resume. Yeah, let's resume. So in this slide is given average rain intensity on the worldwide scale. And yeah, Baltic States region is in this E area, which is yeah, about 22 millimeters per hour. And this value is taken into account for calculations of rain intensity impact on signal quality and radio link operation. Yeah, so for Latvia, its intensity is 22 millimeter per hour. But if we look a bit deep, take a detailed view, then according to some statistical data, using various microwave links planning programs, the rain zone should be selected for almost all territory of Latvia, and for eastern part of Latvia, for Latgale, G zone, and yeah, G is even more, 30 millimeters per hour. Yeah, this 22 is like some uh, ITU data provided such a value. This one are more local data for 2 years period. Yeah, and this values is for 0.01% of the time in year. Yeah. So rain attenuation can be calculated using a TUR outage model, which consists of the following: defining the rain rate for this 0.01 exceeded for this time. Yeah, and these values are defined for 15 rain zones and different time percentages, and they are given in ITU recommendation P.837. Yeah, the link I sent you in the chat, the same recommendation. Yeah, and here is this value for E region for different percentage of time. The values are different. Yeah, next is computation of specific attenuation. For the frequency, polarization, and specific rate using the same recommendation. Yeah, and formula provided here. And in this formula, key contains constants for horizontal and vertical polarization. Constants are slightly different for each polarization. Yeah, and this comes from ITU recommendation. Yeah, P.838. Send link in chat. Yeah, some examples of constants. K for horizontal vertical polarization at some frequency bands 10 gigahertz, 11, 17, 24 gigahertz. And yeah, here given calculation examples, and figure shows the train attenuation is greater for horizontal polarization in regions with higher precipitation. The difference in attenuation is more marked. Yeah, we have 10 gigahertz, 17 gigahertz, attenuation for 11 gigahertz and 24 gigahertz. Yeah, vertical polarization is this orange color, red, orange, and horizontal is with this blue color. And yeah, different range zones. And for example, for E region, yeah, we see that the 10 gigahertz attenuation is more for horizontal polarization. And the same is actually for all range zones. The relation is straightforward that for horizontal polarization, attenuation is higher, and the same is also for 11 gigahertz, also for 17 and for 24 gigahertz. Yeah, difference from 10, 11 is negligible. Yeah, 17, it's within 2 decibels. And for 24, this range is about, I would say, 3.5 decibels, somewhere such limits. And difference between horizontal vertical polarization. Yeah, some 0 something. Yeah, it's differences, but not so big. But of course, if we take longer radio links, for example, 10 kilometers, then this 0 something for 1 kilometers will result in probably in some decibels. Yeah, and this is just for vertical and for horizontal polarization difference. Yeah, and ITU ITU recommends the attenuation determination procedure. Yeah, it's given this procedure given in this slide. First, we find the rain intensity for the needed time percentage. Then we calculate specific losses according to rain intensity, according to ITU recommendation P.838. Then calculate the effective length of the micro radio link. It's according ITU recommendation P.530. Then calculate attenuation. And next attenuation for other percentage time rates if needed. Yeah, according to formulas given in P.530. And the result is the rain attenuation measured as a percentage of time for a given rain region, frequency, polarization, and radio link path length. Yeah, and this specific attenuation can be calculated using formula provided here, where coefficients are provided in the table, and for most used frequencies in microwaves. Yeah, and formulas continues in this slide. Yeah, and next determination of downtime, or sometimes it's named outage due to precipitation. Downtime of the radio link can be determined using a rain attenuation curve as percentage of total system uptime. Downtime is calculated as a percentage of time with an attenuation greater than the loss margin. In figure 7. Okay, basically, in the example, loss reserve was 38 decibels assumed for the radio link pass located in the region L. Length of radio link is 50 kilometers. Frequency is 11 gigahertz, and the used polarization is horizontal. And for this configuration for radio link, downtime caused by rain is about 0.0025%. And downtime detection methods are based on data obtained from long-term rain intensity monitoring and statistics. Therefore, the downtime due to rain should be observed and average over several years. And ITU data comes from monitoring data. There are some global monitoring systems which can do this statistical averaging, but also every country can submit their own data. And that example is presented in this figure. So we have it's precipitation and downtime time is 0.0025%. It's for fading margin should be about 38 decibels in this case. It's for radio link. This for settings. For this case, the calculated value is this one. Other effects of rain. Actually we have this phenomena in the beginning of presentation. There is just some extra information. Next is absorption in atmosphere. So power losses due to atmospheric absorption are usually not so significant and can be neglected in the radio links budget calculation. This effect should be considered only in a certain frequency bands. Frequency bands affected by atmospheric absorption peaks provided in this figure. Yeah, for different frequency bands, here in gigahertz, 10 gigahertz, 20 gigahertz, 15 gigahertz, 100 gigahertz. Atmospheric absorption is different. So for 22.5 gigahertz for water vapor, maximum attenuation is 0.18 decibels per kilometer. It's maximum for this kind of atmospheric parameters, and for frequency 60 gigahertz for oxygen, maximum attenuation is even 16 decibels per kilometer. Yeah, and these values are valid for a particular conditions given in this slide. Yeah, you see for different frequency ranges, the attenuation is dramatically different. Yeah, some absorption calculations. Yeah, so microsystems operating in 22, 23 gigahertz, but are not significantly affected by atmospheric absorption due to the weakening of the rain. In the temperate climate zone, the length of the radio link is usually limited to a distance of 10, 12 kilometers. Yeah. So planning radio links length, it's a signal attenuation need to take into account and calculating budget of radio link. Yeah, and absorption attenuation of water vapor is about 2 decibels, as we saw in previous figure, depending on temperature and humidity, must be taken into account when calculating the radio link budget. 60 gigahertz band is not in commercial use, and this band could be used for very short links, for example, from building to building. And very high attenuation in 60 gigahertz band allows reuse of the same radio frequency channel within a small area without mutual signal interference. Yeah, this is a positive property of this phenomena. At this frequency, it is possible to use the spectrum very efficiently. Yeah, for 60 gigahertz, we see that there is a very large this signal attenuation. Therefore, radio links can be projected at a small relatively small distances for short radio links. And yeah, good thing about this is that at this frequency the interference is reduced between other radio links, so the separation distance between radio links is the separation distance is small in comparison to other radio frequency bands. Yeah, and yeah, this concludes today's presentation about this topic. And yeah, maybe any question. Yeah, and the homework about I mentioned before will be not this time, but I think it will be. I will announce about it next time. Yeah. Um, okay, maybe any questions about today's topic? If there are no questions, then we will take some pause, 15 minutes, and then we'll switch to practical part. Yeah, and this time for Latvian students. Yeah. So thank you for uh, connecting to the lecture, and yeah, if any questions, do not hesitate to contact me. Okay, then now we will go in in pause and return in 15 minutes. Tā, tad turpinām ar laboratorijas darbu. Tad iepazīstināšu jūs ar darba uzdevumu. Tātad šī laboratorijas darba uzdevums būs ieimportēt mikroviļņu punkts radiolīnijas datus programmā HTZ Communications. Un šī uzdevuma ietvaros tiks veidots jauns testa projekts, lai demonstrētu, kā var automatizēt mikroviļņu līnijas datu ievadi mūsu simulācijas programmā. Jā, un tātad darba apraksts ir ielādēts Ortusā, un arī darba faili turpat ir atrodami pie 5. laboratorijas darba. Jā, tad pirmais solis iepriekšējos laboratorijas darbos izveidoto mikroviļņu radiolīniju izmantosim kā avotu tehnisko datu eksportēšanai. To var izdarīt šādi. List, izvēlieties esošā mikroviļņu līnijas ierakstu, noklikšķiniet uz listing un izvēlēties mikroviļņu līnijas datus, kuri tiks eksportēti uz Excel. Tātad jūsu mikroviļņu līnijas datus mēs izeksportēsim uz Excel. Jā, tad ir nākamais punkts failu sagatavošana CSV formātā. Otrs uzdevums, otrs punkts. Mums jāizveido jauns projekts. Projekta gatavošana līdzīgi kā iepriekš. Taisījām projektu. Jā, sekojam šiem te soļiem. Pēc tam trešais punkts. Importējam mikroviļņu radiolīnijas datus CSV faila formātā. Tas izskatās šādi, šāds loks, viņš būs jāpielāgo attiecīgi. Jā, un tad, kad līnijas dati ir ielādēti, tad mēs sadaļā object properties iestatām mikroviļņu radiolīnijas objekta nepieciešamos rekvizītus. Jā, un dati tiks saglabāti programmas iekšējā datubāzē. Tā kā tas ir rakstīts šeit. Jā, nākamais punktiņš ir par datu pārvaldību HTZ Communications programmas iekšējā datubāzē. Jā, un saglabājam tad rezultātu. Jā, nu, šis ir darbs par datu ievades optimizāciju mikroviļņu līnijas datu attēlošanai kartē un datu saglabāšanu programmas iekšējā datubāzē. Jā, nu šis varbūt aizņems vairāk laika kā iepriekšējie darbiņi, bet nu tad jūs, tā teikt, mierīgi varat iziet cauri tiem solīšiem. Jā, nu ja nepaspēsiet šodien, tad arī vēl varēs vēlāk pabeigt. Bet šis uzdevums ir tīri parādīt to, kā var datu ievadi automatizēt, ka nav viss tur jāieraksta ar roku un jāveido tās stacijas, ka ja jums šādu radiolīniju ir daudz, nu, vismaz divas, tad jau ir vērts arī izmantojot šo metodi, jā, kas atvieglos to, teiksim, visu datu ievadi un jā, šeit visi dati tiek ierakstīti vienā rindā, mikroviļņu līnijas dati, jā, un ar roku nekas pēc tam nav jādara. Jā, un tā. Batusā jau es tādu CSV templētu īstenībā jums esmu iedevis, iekopējis. Jā, tā ka paraugs jums jau būs. Labi, darbojoties, ja kādi jautājumi, tad dodiet ziņu šeit, čatā. Labi, tad es.
Principā, uzreiz jautājumu ātri.
Jā, lūdzu.
Es izvēlējos to linku, es paņemu, teiksim, eksportēju uz Excelī tos datus, un man rāda par to linku daudz visādu parametru, un man sanāk vajag no viņiem paņemt, piemēram, pēc tā iedotā jums Excel faila, un tā arī viņus salikt uz datus, ja? Tā es sapratu. Jo tur eksportētajā ir daudz vairāk par 36 parametri.
Nu, jūs varat visus izeksportēt un tad tajā paraugā ielikt, nu, iekopēt tos
Nu, tā
datus.
kā nepieciešamos,
Nu,
teiksim,
jā,
tādā
jā,
ziņā.
jā.
Ok,
Jā,
skaidrs.
tā var darīt, jā. Tā kopēšana no jūsu radiolinka datiem ir tāpēc, ka jums nav cita, teiksim, datu avota, tikai jūsu radiolīnija, ja? Nu, tāpēc tāds workaround sanāk. Bet, nu, šeit galvenais to ideju saprast un zināt, ka, ja vajadzības gadījumā vajag tādu automatizāciju veikt, tad šādi var izdarīt. Jā, arī automatizēt datu ievadi. Un, kad tie dati ir ievadīti datubāzē, tad viņi arī tur glabājas, nu, viņi nevar tur kaut kā izdzēsties, vai ja vien jūs to datubāzi neizdziešat ārā paši.